So we have another problem. We have a drug that is given to patients, and we are asked some questions about it. So we're told that the drug that is given to patients obeys the following dynamical system. Xt plus 1 is, or at least can be modeled by it. Xt plus 1 is equal to A times x of t. And x of t represents the concentration of that drug in the blood after t days. And what we're given here is we're given the initial concentration x naught and the concentration after 1 day x1. All right, first off, we need to find the value of a. Well, it's pretty obvious to see that in each case, for each patient, we basically half the concentration, right? It gets halved. So from 1, it goes to 0.5. From 1.5, it goes to 0.75. From 4, it goes to 2. It's pretty obvious that a is equal to 1/2 because we get a 50% reduction. But if you had weirder numbers and it wasn't so easy to see, given that your system is x of t plus 1 is equal to a times x of t, all you do is you want to solve for a, right? So it's x of t plus 1 over x of t. And in this particular case, you're given x1 and x0, which is convenient because this is going to be equal to that, right? You just set t equal to 0 if you wanted to be technical about this, right? For t equals 0, then you get x1 over x naught, because this will be true all the time. This is true for any t. But in this case, you do x naught over x1 over x naught, and you take any of these guys, any patient, say I take the first one, 0.5 over 1, and I get, oh, my value of a is 1/2. Okay, so either way, however you want to calculate it, if you spotted, good. If not, this is how you do it. You can calculate pretty easily that a is 1/2 because the model is so easy. It's just xt plus 1 is equal to a times x of t. Solve for a. A is just the ratio of these two guys in this case, and then you just need 2 points. So we pick we pick these 2 points because they're the points that are given to us, and we find what a is. All right. For patient 1, how long will it take to reach a concentration below or equal to 0.05? That's pretty easy to do. We can just use the general solutions to remember that when f of x, the updating function is of the form rx plus d, and that implies, by the way, that your equilibrium is d over 1 minus r. Okay, the general solution is going to be of the form xt is equal to r to the t times x naught minus x star plus x star. In this case, okay, what's x star? Well, in our model, remember that our model is just ax of t. The d over here, the d is 0. So therefore, right, because I can write the model as a times x of t plus, well, 0, because we've got nothing. So x star, the equilibrium, is just 0, right? Because our updating function here, I suppose I should have written it, is going to be ax. What's a? It's 50%, it's half, right? So our updating function is x over 2. What's the value of d here? It's 0, so that's why our equilibrium is 0. Okay, and what's our initial value? What's our initial value? Well, for patient 1, our initial concentration is pretty easy. It's 1. And so we plug that into this, and we get that the general solution, x of t, is going to be 1/2 to the t, and that's it. And now you want to know for which value of t the concentration is going to be 0.05, so just set it equal. Set x of t equal to 0.05. Okay, so now you're solving for t, 1/2 to the t. All right, you can just take the log base 2 logarithm of both sides. So you get log base 2 logarithm of 0.05. You can actually take the log base 1/2 logarithm, but that's going to, it might be a trouble to enter it on some calculators. So I'll just take the log base 2. And so log base 2 of 1/2, if you use the log rule to split it up, you're going to get log base 2 of 1 minus log base 2 of 2, right? It's the rule log of a over b is equal to log of a minus log of b. And I split this up. What's log any base of 1 is just 0. So this is going to be a minus. And log base 2 of 2 is going to be just 1. So it's going to be minus 1. So I get t is equal to minus log base 2 of 0.05. And if I go ahead and I calculate that, log base 2 of 0.05 with a minus in front, I get 4.32. So it's going to take me 4.32 days to get rid of that, to get rid of the drug concentration all the way to 0.05. All right. So how long, so question part C, how long does it take for the concentration to decrease by 40%? Okay, so we want to decrease the concentration by 40%. Okay, and I suppose we'll do it for an arbitrary patient. Why not? So let's just say x of t, right, is going to be 1/2 to the t times x naught minus x star plus x star. What is x star? In this case, it's 0, right? And this, by the way, is the general solution for any patient. The reason it's for any patient is because we didn't specify the initial concentration, right? The only difference between all these patients, 1, 2, and 3, and whoever else, is the initial concentration. The dynamic system is the same. The equilibrium is the same. It's only the initial value. So it's this value that's the same. And in the case of patient 1 that we did here, we used the case of patient 1, x naught was 1. Okay, but in this case, it's just x naught. But it actually won't matter what the initial concentration is. So all we want to do is we want to decrease the initial concentration by 40%. Okay, that's the question. How long does it take for the concentration to decrease by 40%? So this is the key. To decrease by 40, that means that there's 60% left, right? If something decreases by 40%, that means you got 60 of it left. I can't spell, by the way. Okay, all right. So that means that we have 60% of it left. So what's the, this is what we're going to put into our equation here. What's x of t? Well, x of t is going to be 60%, so 6/10 of x naught, right? What this means is 60% of initial concentration. And we set that equal to 1/2 to the t times x naught. Why do we do this? Because we're asking the question, when is our concentration, right? X of t gives us our concentration as a function of time. And we set that equal to this thing because this is asking the question, if we set x of t is equal to 6/10 x naught, that's asking the question, when is the concentration x of t equal to 6/10 x naught? That's the question we're trying to find, right? We're trying to find for which t does this hold true? For which t do we have 60% of the concentration is the concentration that is remaining? That's what we're trying to find. And so when we do this, you'll actually see, oh, look at that. The x naughts, they cancel, so they actually do not matter. And what we get is 6/10 is equal to 1/2 to the t. And if you go ahead and solve this, okay, you go ahead and solve this, you will get t. And I'm just going to give you the straight answer right over here. If I go in and solve that, I will get 0.74. 0.74 days. So within a day, we actually lose 40%, which makes sense, right? It makes sense that the answer is less than 1 because we know that it takes 1 day, or sorry, it makes sense that the answer is less than 1 day. Yeah, it takes less than 1 day because we know it takes 1 day to reduce the concentration by half. Okay, but we're only trying to reduce it by 40%, which means that it should take less time than a day. Because if we had more time than a day, that means we would have more than half that was gone. All right, so that's this part. And now, all right, we want to assume that the patients are given an additional dose every hour. So this modifies our system, right? Our system before was xt plus 1 is equal to axt. Now we add a constant dose every, we'll make it every day, sorry. An additional dose be not every hour. Here, we'll make it, because that's going to complicate our system. We're going to make it every day, okay? An additional dose every hour such that x of t is plus 1 is equal to axt plus b. How large should b be for a steady concentration of 0.5? It actually wouldn't matter if we added it every hour or not in this particular case, and I'll show you why. Because if we look at our equilibrium, right, because what do we mean here by steady concentration, right? Steady concentration is just the equilibrium. So we want the equilibrium concentration, we want that to be 0.05 or 0.5? 0.5. we want this is what we want. This is what we want. And we know that the equilibrium x star is going to be d over 1 minus r for a system f of x is equal to rx plus d. In this case, however, instead of calling it d, we call it b. All right. So this guy's going to be called b. This guy's going to b is now d, or d is now b. Okay. And we want just to find what b is so that x star is 0.5. We could just solve for it. B is therefore going to be 1 minus r times x star. R is 1/2, so it's going to be 1 minus 1/2. X star, we want it to be 0.5, so it's going to be 0.5 times 0.5, which is going to be 0.25. Okay, how did I find that again? Here's just a quick recap. I know my equilibrium concentration, x star, is going to be b over 1 minus r. Okay, this is for a time dynamical system of the form f of x is equal to rx plus b. I know that this is going to be my equilibrium. I want the equilibrium. I want to find b. I want to find b such that my equilibrium is 0.5. So all I do is I plug in 0.5 into the equilibrium and I go ahead and solve for b. And as far as why it doesn't matter if we add this dose b every hour or every day or every second day, is because the equilibrium concentration doesn't depend on how many times or how often you introduce this b here. As long as it's recurring, as long as it's being constantly added, it'll always reach the equilibrium. So that's a neat thing about the equilibrium, that it doesn't depend on like whatever t means, like the delay, whether it's a day or whether it's a month or whether t means a second or a minute. The equilibrium is not going to be affected by that. It's not going to be also affected by the initial value. So if you ever find yourself given a system and you're not given an initial value or something, and you're thinking, oh, how am I going to find the equilibrium or the stability of the equilibrium, just know that you don't actually need to know that to find the stability of the equilibrium. All right, or to find the equilibrium. Okay, so hopefully that helps.